So hello students, in this lecture we will see the types of solutions of linear programming problem when we solve it by graphical method. Generally, we have three types of solutions here. One is alternate solution, that is we get more than one optimal solution having the same optimum value of the objective function. Second type is unbounded solution. Here we get unbounded region and hence we cannot find the answer or the optimum value for the objective function. And third is infeasible solution. In this, there does not exist any common feasible region. So, solution of that LPP does not exist. So, let us see this. So, in this first example, we will see about the alternate solution. So, the example is maximization Z 4x1 plus 4x2 subject to x1 plus 2x2 is less than or equal to 10, 6x1 plus 6x2 is less than or equal to 36 and x1 is less than or equal to 6 along with that positivity constraint. Let us draw the graph of this. As we know now how to draw the graph and how to find the solution, we will find it. We will go to this now. Okay. So my first constraint is x1 plus 2x2 is less than or equal to 10. X1 plus 2y. Now here we are using x and y against x1 and x2 respectively, less than or equal to 10. Yes, so we have this line along with its feasible region. Next constraint is 6x plus 6y is less than or equal to 36. You can divide throughout 6 to this constraint and can draw this constraint. So here also we have drawn the second constraint. Next constraint is x is less than or equal to 6. X is less than or equal to 6. So now here we can see, so as both means the x is greater than or equal to 0 and y is greater than or equal to 0. Obviously this region here, this region is our common feasible region which lies in the first quadrant. Okay, so how many coordinates are there for this? This is one coordinate which has vertices for this, so which has coordinates 0, 5. Here now you can see the graph and as we can see here clearly that the coordinates of this vertex are 2, 4. Yes, so here you can see this 2, 4, right? And for this only 4 coordinates are there. One is origin, then this is 0, 5, then this is 2, 4. This coordinate can be coordinate of this vertex can be obtained by solving equations 1 and 2. This because it is the point of intersection of first and second constraint. So solving it simultaneously, we will get coordinates of this vertex as x equals to 2 and y equals to 4. So as this in this graph we can see it clearly. We can say now here that the coordinates of this vertex are 2, 4 and this one is 6, 0. So if we find solution of this means value of the objective function at this point, then let us see uh, what we are getting. So now we have obtained the vertices here. So one vertex was 0, 5. So value of z is 20. Another vertex which we have obtained by solving equations 1 and 2, this constraints 1 and 2. In the previous lecture, we have seen that how to find the point of intersection of these two constraints, two lines, and how to get the coordinates, right? So coordinates of these points are 2, 4, and value of z is 24. Also, the third vertex was 6, 0. See, 6, 0, and value is again 24. And last was the origin. Obviously, the value is 0. Now, as this example is of maximization here, this maximization, we will choose the maximum value. Now, we can see here in the table in the column of z that there exists two same maximum value of z, but at different values of x and y. Okay, so here at x equals to 2, at x equals to 4, we are getting the same, means we are getting the value 24 here. Okay, here, this, at this point x equal to 2 and y equal to 4, value is 24. But at x equal to 6 and y equals to 0, same value we are getting. It means that it has alternate solution, but at different values of x and y. So this can be there. So this is the case of alternate solution. So therefore, first optimal solution we can write that x1 equal to 2, x2 equal to 4, and z max equal to 24. Or we can say that this is also the another optimal solution for this z. So in this way, this has more than one optimal solution. Hence, it is the case of alternate solution. So this can happen here. Also, in the simplex method, it is the case, because as it is a LPP, we are solving LPP by simplex method. Same. Then we can get all these three types of solutions in simplex method also, but the criteria are different here. So this is the case of alternate solution. Let us go to the next type of solution, which is unbounded solution. So here is the example. Let us see this example. What is it? Maximization of 2x1 plus 3x2 subject to this constraint that x1 minus 3x2 is less than or equal to 6. 2x1 plus 4x2 is greater than or equal to 8. x1 minus 3x2 is greater than or equal to minus 6. And obviously, this last constraint is positivity constraint. So now let us go to the graph. Let us start for the new graph. Okay. So my first constraint is little bit small. We will do this so that we can see the graph properly. So the first constraint is x minus 3y. Now here we are considering x and y corresponding to, means 6. Okay, so this is the first constraint and its respective feasible region. Second constraint is 2x plus 4y is greater than or equal to 8. Yes, we are getting this feasible region for this line, and automatically it is forming the common feasible region. Next constraint is x minus 3y is greater than or equal to minus 6. And obviously, if you observe, we will have to consider it due to the positivity constraint. It is from the first quadrant. And if you see the common feasible region in the first quadrant, then here this triangle we will not take because it comes in the fourth quadrant. So the common feasible region, let me plot the points of this. Here I can draw. I can plot the points. This is the first point. Then I'll change the color of the point. Okay, then here this is the second point, then this is the third point. And now if you observe here, this whole region here, it is going to infinity, and this is the common feasible region. So here it is not the case that we are not getting common feasible region. We are getting here the common feasible region, but this region is unbounded. Now let us check what is our objective function. So our objective function is here in this example maximization, right? So if it is maximization, here we should get some bounded region so that we can check the boundary of the value of the function. But here it is going to infinity, as there is no any boundary, it has unbounded region, and hence this example has unbounded solution. Suppose here the objective function is of minimization. Okay, if it was if suppose that it was of minimization, then there exists the solution, because minimum value lies at the boundary points of the example. So though we are getting unbounded region, and if your objective function is minimization, then we get the solution. But here, as objective function is of maximization, and as the region, common feasible region in the first quadrant is going to infinity, here there is no end, there is no any optimum value, no end, it is not ending somewhere. So this linear programming problem has unbounded solution. So we can write the solution in this way. The common feasible region of this LPP is unbounded. Hence, Z max means value, maximum value of Z does not exist. And therefore, what is the conclusion? Hence, the conclusion is that this linear programming problem has unbounded solution. So after getting the graph and the region, you can write the answer in this way if that linear programming problem has unbounded solution. So first case we have seen as of alternate solution, where we are getting more than one optimum solution, and this is the second type of solution, which is unbounded solution, where we are getting the unbounded common feasible region, and as the objective function is of maximization, we are saying here that this LPP has unbounded solution. If it have minimization, then here we would have get the answer. But as the objective function is maximization, we are saying it as unbounded solution. Let us go to the next type of solution. The next type of solution is infeasible region, not region, infeasible solution here. So infeasible solution means what? It does not have any solution, means no common feasible region. So let us consider this linear programming problem. It is maximization of 2x1 plus x2 subject to the constraints 1.5 x1 plus x2 less than or equal to 6. Second constraint is x1 plus x2 greater than or equal to 7. Then next constraint is x1 is less than or equal to 2. And this one is the next constraint, minus x1 plus x2 is greater than or equal to 4. And here it is the positivity constraint. Let us go to the graph again. So let us see again that constraint. First constraint is 1.5. It is not actually 1, 1.5 it is. Actually, it was of 3 by 2. 3 by 2. So here it was 3 by 2. So I have written here it is 1.5. Plus x2 is less than 6. Okay, there are total how many constraints? 1, 2, 3, 4. So we should have 4 lines. Okay, so let us go to the graph. We will consider the new one here. Okay. So what was our first constraint? 1.5 x plus y is less than or equal to 6. This is the line. and its corresponding feasible region, and this is x plus y greater than or equal to 7. Okay. So here is the second constraint along with the first constraint. X1 is less than or equal to 2. So here x is less than or equal to 2. X plus y is less than or equal to 6. X plus y is less than or equal to 7. Say that which one to be considered, that this is the common feasible region or this is the common feasible region. So we cannot consider any common feasible region here. So we can conclude that for this linear programming problem, there does not exist the common feasible region. And hence we cannot find actually the optimum solution, as the example is of maximization. Again, it is going to infinity here, this side and this side. So obviously it doesn't have the common feasible region. So how to write the answer for this? So for as from the graph, we can conclude now the common feasible region for this LPP does not exist, and hence this LPP has infeasible solution. Infeasible means what? No solution. So here this LPP has no solution. So thus we have discussed all these three cases of the types of solutions of the graphical method. One is first alternate solution, then unbounded solution, and third is infeasible solution, right? There is one more concept here in this graphical method, that sometimes some constraint means here, I'll show the graph here. So suppose here we have this region, and just neglect this. Suppose now suppose for this example for a moment that assume that this part is not there, these two lines are not there. Okay, so here this is our common feasible region, and suppose there is one more line lies like this here, this side. Okay, here, so I'll I can draw the line. So now I am changing the line actually. Okay. Okay. So suppose I have this line and its common feasible region is again this side. Okay. But here, though we have this line which is a part of the constraints, but we if this line is not present, then there is no any change in the common feasible region. So such type of constraints here, which is the part of linear programming problem, but which do not contribute in the common feasible region of that linear programming problem, is called redundant constraint. So that is a concept of a redundant constraint. That is, it is a part of LPP. It is a constraint, one more constraint, because it is a data. It is not only the mathematical examples. Here we are seeing that these are the mathematical examples, but actually these are the case studies, and after that case studies, the model has been constructed, that models we are solving actually. So this is one more constraints, but it doesn't make any effect on the optimal solution. Though it is present over there or absent over there, there is no any problem uh, uh, on the optimal solution. So such constraints are called the redundant constraints. So that is one uh, more characteristics of that constraints. And here the type of solution we are considering this linear programming problem. So here we have seen all about the graphical method. Now you can write these examples and you can practice these examples. Copy it, give 2 minutes.